Voltage stability enhancement using FACS controllers dependent on voltage stability indices. Abstract increased load demand, mostly reactive load, and insufficient generation sources have caused the power system to work near its point of voltage uncertainty. For many researchers, the question of evaluating voltage stability prior to voltage failure has become an exciting topic. Therefore, several voltage stability indices have been suggested to measure the distance of the power device from voltage failure. In this article, two line indices of voltage stability have been carried out. The index of line stability, and the index of rapid voltage stability are, FVSI. They were used to govern the weakest bus in the IEEE 30 bus test process. Then, three kinds of FACS compensation, shunt, series, and hybrid, shunt and series, were used to assist voltage stabilization. The results indicate that shunt compensation is more effective than the other two forms. Keywords: voltage stability indices, FACS compensators, line stability index, fast voltage stability index FVSI, voltage stability enhancement, IEEE 30 bus system. Introduction. Voltage collapse is the mechanism by which voltage instability in a significant part of the device results in voltage loss. 3. Adding extra reactive power by implementing reactive power sources is the best method to improve the voltage stability boundary, i.e., FACS controllers at the right venue. FACS devices are made up of shunt, sequence, and hybrid parts. To define system voltage stability problem, the component's correct choice will restore the system's voltage stability. 1. In voltage stability analysis, scalar magnitudes that can be tracked as device parameters change are useful for estimating power systems' voltage stability using voltage stability indices, VSI. Operators can use this index to know how close the device is to the voltage failure in an accepted way and respond accordingly. 7. The application of two voltage stability indices to an IEEE 30 bus test system is described in this paper. For the identification of the weakest bus in the scheme, the efficacy of these indexes was compared to. Moreover, the addition of shunt compensation to the weakest bus is helped by comparison the voltage profile of the system and steady margin for state voltage stability. The paper also includes shunt, set, and hybrid FACS compensators, shunt and series. This paper's structure is as follows: mathematical formulation, simulation tools used for the analysis, then finally results and conclusion. Mathematical formulation of the indices. In up-to-date power systems, voltage stability indices can show the voltage stability state of a power system. These indices were used to locate the power system's critical bus, or to measure the voltage stability margins of the system. 11. Two-line voltage stability indexes are described briefly in this section and are used to evaluate system stability. Index of line stability. The index of line stability was introduced in 1998 by M. Mogavemi and F. M. Omar 10. It is based on the principle of power transmission on a single line. The application of this index can provide the ranking of the tested system buses. This index's lower value means higher stability. As the index's value rises to reach unity, it should be said that the line is closer to its instability. 6. A single line of a unified network is shown in Figure 1, where LMN is derived from Figure 1. Is the line impedance angle, and is the angle difference between the sending end and the receiving end voltage. In 5, lines that displays values of near to 1, specifies that those lines are closer to their unpredictability points. However, the index should be less than 1 to maintain a safe condition. Fast Voltage Stability Index, FVSI. Quick Voltage Stability Index FVSI as proposed in 2002 by I.Musarin and T.K.A. Raman 12. The features of this index can provide the rating of the tested system buses. Similarly, smaller value of the index indicates greater stability of the voltage. As this index's value rises to reach unity, this indicates that the line is closer to its point of instability. 8,4. The index of stability is QJ, is the reactive power flow at the receiving end, and 6 is the sending end voltage. The line that gives an index value close to 1 would be the crucial line for the bus. It also contributes to the instability of the entire system. It is possible to use the measured FVSI to evaluate the weakest bus in the system. The concept of the weakest bus depends on the maximum allowable load on the bus. The most vulnerable bus in the scheme is the bus with the lowest overall permissible load 9. Simulation tools. The IEEE 30 bus test system is the system studied in this article. Figure 210 displays a single line diagram of the test system. The system is composed of 5 generator buses, 24 load buses and 41 interconnected lines. The details of the test system are given in 5. Gauss Seidel is the load flow process, which is an easy and unnecessary amount of computing time. Using MATLAB M-file, the load flow programmers were completed. Results. Rank determination of the weakest bus. The rank of the system buses needs to be determined by improving voltage stability. The weakest bus in the system, which has the lowest maximum reactive capacity, is given this rank. Figure 3 displays the flow chart of the software to assess the weakest bus and the load bus range based on the 2 FVSI and indices. Moreover, the maximum reactive power of all the load buses corresponding to the 2 indices is calculated. Running the load flow software is the first step. The device parameter that was obtained was used for the index calculation. The freight buses are checked one at a time. In each stage, the reactive power on the tested bus is gradually raised by 0.01 MVAR. When the index reaches 1, the programmer progresses to a new bus. Only the reactive power on each load bus is modified incrementally. The key explanation for the voltage failure may be that the power system cannot supply the reactive power or an intemperate absorption of the system's reactive power aid. From figure 5, as is obvious, the bus voltage decreases with increasing reactive power. Also, as reactive power increases, the value of the indices of the 2 lines increases. Also, line 29 to 30's FVSI hits its limit, 1, at 25.9 MVAR. Constant power factor load changes. In practical power systems, the actual and reactive load generally differs from the same percentage. This means constant power. It is, therefore, assumed that as the load increases, the power factor remains constant. The index of voltage stability is determined by increasing all load buses to a constant power factor 9,3. The loads are raised in steps before the system's load flow diverges. The system's voltage profile for the base case and 1.5 load factor is shown in figure 6. From this statistic, it was evident that bus 30 is the weakest bus, as seen in the previous section. The figure demonstrates that at heavy loading conditions, the voltage at bus 30 decreased to 0.89. The variance of FVSI indices of the 2 lines linked to bus 30 with the loading factor is shown in figure 7. Until the load flow solution no longer converges, the index increases with the loading factor. The values of the indexes are within the boundaries of equilibrium. With different FACS compensators comparison system performance. The best location for the addition of shunt compensator bus 30, the weakest bus, is providing reactive support for shunt. For different values of reactive power compensation at bus 30 with full reactive power load, Table 3 represents FVSI and per unit bus voltage, 25.9 MVAR. The thyristor-controlled series compensator, TCSC, is added to the series compensator, to the 27 to 30 line, which is the best position for series reimbursement. Different TCSC values, Table 4 reflects FVSI and per unit bus voltage. Shunt compensation on 30 bus is added on all shunt and sequence compensators. In addition to that, series compensation is applied to line 27 to 30. For different series values and shunt compensation, Table 5 represents FVSI and per unit bus voltage. With shunt FACS controller system performance. Clearly, at bus 30, the weakest bus in the system, the appropriate place to have shunt reactive backup is The shunt fax controller's capabilities can be calculated by adding such reactive power increments before the voltage on this bus becomes 1 pu. It has been determined as 15 MVAR at 1.5 loading factor, for instance. The voltage profile of the device at 1.5 loading factor with and without shunt fax is shown in Figure 8. Conclusion. Recently, several voltage stabilities indexes have been presented. These indices are used to show the collapse distance of the voltage stabilization form. To discover the weakest bus in the IEEE 30 bus test system, two of these indices, the Line Voltage Stability Index, LMN, and the FVSI Fast Voltage Stability Index, are used. The findings suggest that the worst bus is bus 30. This bus is the best shunt recompense spot. In the first test, a fact involves a shunt to increase bus voltage and series to reduce line tension. In the first test, fax compensators are linked to the weakest bus. The fax part is linked to the weakest line in the second test. The fax components in the third test are related to the weakest bus and the weakest line. The results show that the best improvement in voltage stability is given by shunt compensation.